Good morning. I don't know why students are not coming to class. We are now on to start the last chapter or the last unit in the syllabus, which says logic families. Now, these logic families or logic circuits or IC logic families or digital integrated technologies, everything means the same thing. There is no difference. It basically talks about some internal details of a gate and how a gate is going to respond. So far, what we did is we had been using symbols and we never bothered what is inside it. Okay. In first year electronics engineering course, though you have done a bit of it, but I am still doing all the repetition because I know most of you did not attend the classes and most of you would have only copied the assignment and wouldn't have done it. Okay. Nevertheless, I am repeating it. Kindly review and sorry. Sorry. One thing is classification. These families can be classified in various ways based on various things. There are some classifications which are based on number of devices on a chip. And there are based on type, or technology, blah blah. There are various ways to classify it. We will not go into the um, kind of this problem of classification. We will only do classification based on the type of basic devices being used. This classification we are using, and on this basis we are saying I have two group of families. One is BJT based, another is MOS based. So what does it mean is BJT based technologies are going to use your NPN, PNP transistors, which are bipolar transistors, bipolar junction transistors, and in addition they can use diodes, either normal diodes or Schottky diodes. Okay, and MOS based technology will use MOSFETs. So you can have N MOSFET, which means N channel metal oxide semiconductor field effect transistor, or it could be P MOSFET. So, but even then there are varieties of these two devices. A variety, not exactly the variety type, I should say. There are two kind of N devices and there are two kind of P devices, and we will see what is used where, what they are. Only a brief introduction I'll tell. Okay. Let me first tell you, when you talk about BJT based technologies, you have various technologies starting from RTL. Sorry, I have some cold and therefore some problem. RTL means resistor, transistor, logic. That means all gates are drawn using resistor, transistor. There could be any number of resistors, any number of transistors, depending on what gate I am going to draw. Also remember, every technology does not make every gate available as a basic gate. Only some of the gates can be drawn as basic gates, and others are derived gates, which means that they are made by using two primary type of gates or two basic gates. So, not every technology will allow you to draw every gate as a basic gate. We will go into some details to see what is a basic gate later on. Yes, Tanya. Second kind of technology is DTL, where you make use of diodes, transistors, and to realize a gate. So it is called DTL, diode transistor logic. Then you have transistor logic, TTL. This is by and large the most popular in this category, most popular and widely used uh, logic family in BJT category. Okay. Then you also have ECL. You also have I square L, which means IIL. Okay, these are various technologies which are commonly available, but by and large, this is the most popular. But this you understand if you have understood the implementation RTL and DTL, then only you will be able to appreciate TTL. And all these technologies will require you to have basic understanding of BJT, which means what are the switching characteristics of a BJT, that should be known to you. You had done even a experiment on switching characteristics. Revise it. How does it behave? Okay, in the switching characteristics, what are the switching characteristics of BJT? Even you should know the characteristics of a diode. When does it conduct? When does it not conduct? Okay, what is the barrier potential of the diode? What is the role of being a silicon or germanium diode? So what is going to be the drop across the conducting diode? Similarly, for BJT, you will have two junctions will come in. Yes, please. Tanya, bolo. Tanya Sood. So in a bipolar junction transistor, you have two junctions. Okay. Again, you can have a silicon transistor or a germanium transistor. So I do expect that you know the characteristics of a transistor, the switching characteristics of a transistor, and also the IV characteristics. Okay. So that I can't do all the device physics in the course. So this is a presumption before we start talking about these circuits. If you even don't know what is the drop across a junction, what is the V on when a transistor is conducting. For example, let's say this is a one of the BJT, okay, NPN or PNP, identify. It's NPN, huh? So if this transistor is on, what is this voltage across the device? Okay, what is the minimum voltage required over here to turn on the device? All these operating characteristics should be known to you. So kindly revise your BJT and diode. Okay, I am sure resistance, how it works and behaves, everyone remembers easily. So we primarily will be talking about TTL technology, and for this you require a prior knowledge of RTL and DTL. These two we are not going to discuss at all. Okay. In MOSFET, if I talk, there had been three technologies so far. One is, sorry, I should write it. One is PMOS technology, then it was NMOS technology, and now for last 30 years it is CMOS technology which is prevailing. Not just 30, I believe 35 years or so. So for last 35 years, this is prevalent. But the first technology, the first MOS technology was PMOS technology, and then came NMOS technology, and then CMOS technology. I can give you a brief history. Why PMOS came first, what it consists of, NMOS, etc. First, let's see what is PMOS uh, having. PMOS technology made use of two devices which were P channel MOS transistors. Both were P channel MOS transistors. One was the enhancement type, or which worked in enhancement mode. Another was a depletion mode device. Okay, now enhancement mode device is normally off, and when you apply a VGS which is less than VTP, then it turns on. Okay, whereas depletion device is normally on and it turns off only when you apply a VGS greater than VTP. Then it will turn off. Okay, so see, their behavior is different. On some situations, you use a normally on device and you only turn off conditionally. And some devices are uh, normally off, and if you want to switch them on, you have to apply a higher voltage. Now, what happened is this PMOS typically was, let's say, is working on 5-volt VDD, and VSS or ground is typically 0 volt. So you have, this is not a dot, okay, 5 volt and 0 volt. Okay. Now see, the voltage you can apply on any node is between 0 to 5. These are the voltages available. So if I draw a PMOS, This is my PMOS transistor. Let's say this is source, gate and drain. Okay, so typically if you are drawing a gate, this source will be at higher potential. It's always at higher potential, but typically it will be connected to VDD, and this will assume some voltage, and this is the gate potential which you are going to connect. Now the VT of a PMOS transistor is typically a negative value. Okay, so if it is a negative value, you need to apply a VGS which is more negative to turn on a enhancement mode device. This is the typical enhancement mode device. If you have a depletion mode device, it is denoted by a additional line in the channel which says the channel exists normally. If you want to remove this channel, since it is a p-type channel, so positive or charge carriers, which is holes, is accumulated over here, or are appearing already present over here. So you need to apply a positive potential over here. So earlier you were applying a more negative potential. Now you will apply a positive potential, and typically the threshold voltage for this device will be positive. Okay, so you need to apply a positive value higher than the positive value of the threshold value which is available over here to turn it off. Okay, and you will not be able to apply a positive value because this, if connected to 5 volt, you do not have in your system to apply a higher 5 volt. So in this logic family, basically these devices were used instead of a resistance, which are all always on, and they offer a on resistance of the device. So these devices were not switching, but these devices were offering a resistance. So I'll go to the basic detailing of the circuit, then I will explain how it is used as a resistor. Okay, in NMOS technology, the difference is you have only N-channel MOSFET transistors, but of the two kind, enhancement mode and depletion mode. Now here, the this device, enhancement mode MOS, PMOS, NMOS device will have a positive threshold value, okay, which will be normally the device will be off. If you apply a gate potential or effective gate potential higher than the VT of the device, then the device turns on. In depletion mode device, the threshold voltage of N channel transistor will be negative value. So if you apply a more negative value, then only it will turn off. Okay. And in CMOS technology, you were using only NMOS and PMOS, one NMOS and one PMOS devices, both of the type enhancement. Okay, detailing of all these things you are going to do in your course MOS IC design, which appears I think in 5th or 6th semester. So when you have this course MOS IC design, you will study all the detailings of CMOS and NMOS logic. Okay, why first PMOS came? Now you will remember one thing. Now this PMOS has a mobility or the current due to holes, and this is due to electrons. Okay, and electron mobility is much higher than the hole mobility. So this has less conductivity as compared to NMOS device, and therefore PMOS is a slow device, NMOS is a fast device. But even then, first technology which came up in the market, the first MOS technology was PMOS, and it was only due to ease of fabrication. This has all the disadvantages of its speed and making a bigger transistor, all that stuff. But at that time, to begin with, can you fabricate? That is the most important issue. Modeling is not enough, simulation is not enough. You should be able to make that device. So NMOS was difficult and was not getting a good quality device, but PMOS was the first one which was a good quality device which could be made. And the first microprocessor, which is 4004, Intel microprocessor 4004, was used this technology, and I believe it was somewhere in 73, 74 time frame, 1973, 74 time frame. I'm not 100% sure, around that time. But the next IC which came up, because microprocessor and memory are the leading ICs in the digital domain of technology. 8008, this was the next processor, both from Intel. Intel used to be the leader at that time. And this was using a NMOS technology. So by that time, NMOS technology was stabilized, and this used a NMOS technology. And if I am not wrong, this was something like 10 micrometer technology even at that time. And this was in late 70s, 2 3 years down this line. Okay, remember what was the technology? 10 micrometer, that means the gate channel was length was 10 micrometer. Any line which was drawn on IC was at least 10 micrometer. Nothing was less than 10 micrometer on chip. Okay, it was in 80s, early 80s, I believe 1984 or somewhere like that, when CMOS technology came into the market and captured all the market since then. So it is more than 35 years or so since. And in my career, I have seen throughout CMOS. I started working in 1988. And I did test one NMOS technology chip, but all the chips which I designed and got fabricated were using CMOS technology. And by this time, the CMOS technology was established. And around this time, it was still 3 micrometer technology. Anybody who knows what is the current technology, you can send me on chat, or you can unmute yourself and speak out. If anyone has an idea, what is the lead technology of the day?
And 5 nanometer.
Yes, very good. It's around 5 nanometer. There is one chat comment. Let me, yeah, it is the same. Five, some people are using 7 as a commercial technology, and some are also starting to use 5 nanometer. Beautiful. So see, 3 micrometer to 5 nanometer, you have 10 to the power 3. This is the degree of difference from 88 to till now, how the technology has moved. A scale of 1000, almost 1000 times smaller devices are available. And which also means that, see, if this was my device and now your device is 1000 times smaller, that means you can pack that this many time more devices into the same area. Okay, and this is a huge number. So today technology offers you a, a space for numerous devices. Whatever number you put, area is no longer an issue. So we will talk about what are the primary characteristics. When you talk of an IC, you are talking about overall. So you talk about speed, you talk about power, and you used to talk about area. These used to be the three criterias to begin with. And I also remember I tested one chip which was NMOS technology chip, PWM controller, which was designed and fabricated in 1987. And when I joined in 88, it was kind of fabricated, and it was packaged and it reached. So I tested first. That was the first chip I tested. So that chip had to be done as a pair of chips, because in one chip, the whole logic could not fit. Today, these kind of issues are not there. You have a capacity to fit in of the order of 2 billion transistors on same chip. What is lacking today is a application, a design application. How do I make use of this many devices and do a meaningful operation which is viable in the today's market? Okay, today people are able to fabricate the whole system on a chip. Okay, so all those things are happening. But let's come back. Now we were talking about the families, the various families which are available to fabricate your basic gates. What are the basic gates? The universal gates, NAND NOR gates, and other basic gates are AND, OR, invert, XOR, XNOR. These are your basic gates which you use to realize any functionality. The number of inputs, there could be 2 input gate, there could be 3 input, 4 input. So how many inputs can a gate have? How do you decide? How does technology decide? Or which technology is better? If I want to use, I want to design a circuit for given constraints, how do I pick up a technology? Or how do I compare the various technologies available to me for a design? So this is known as basically the characteristics, the parameters which characterize. So I am writing them as IC characteristics. And I must know what are the parameters which characterize a given IC, and then only I know whether I can utilize it for my given application or a function or not. Okay. So to begin with, there are various characteristics. We will talk about some of those properties. First thing, power and ground. What are the values of my power and ground? It's important to know, because maybe you are picking an IC for a system. If system is operating on, let's say, 5 volt, and you use an IC which works on 12 volt supply, it will not fit in. I cannot, by no means, I can generate a high power on in the system to get it. Okay. Though if I'm using a system which is basically operating on 5 volt, but I have an IC which is 3 volt, if I connect a 5 volt to this IC can burn off. It will not behave as the predicted behavior of the IC. So but I can use a, you have voltage dropout circuits which convert your power supply from one value to another, but it's easier to lower the value, so you can bring it down to 3. So you need a, what do you call it, LDO. LDO, you need to use an LDO before that chip to drop down the power. So, but it's important that I know what is the power of my IC. So this is one characteristics. The second important characteristics are the logic levels. You remember? You would have done it in electronics engineering. Do you remember? Yes. Anybody? हाँ या ना, कुछ तो आंसर आना चाहिए ना. चैट में ही लिख दो अगर बोल नहीं सकते तो, या नाम भी नहीं सुना. Okay, I'll need to pick up somebody. Yeah, the first name which is appearing on my screen, Tarun Kansal. Tarun Kansal, unmute yourself. So he is absent. Let me record it. Tarun Bansal was absent today. Akash Deep, if you do not turn on your mic, I'll assume you are only connected but not present. Yes, Akash Deep, do you remember this line, logic levels, voltage ranges, which are the characteristics of the logic families?
No, ma'am, actually, I don't remember it.
Okay, no problem. Aditya Chawla,
Yes, ma'am.
do you remember this reading in electronics engineering?
No, ma'am.
क्लास लगाई थी?
Yes, ma'am.
सारी क्लास लगाई थी?
Yes, ma'am. Last year सारी
तो
लगाई
उसमें
थी.
पढ़ाया नहीं तुमको?
हम याद नहीं पढ़ाया था तो मतलब.
बच्चे याद रखना शुरू करो, अगली
अच्छा.
क्लास में फिर बोलोगे कि मैडम ने नहीं पढ़ाया था.
No, ma'am, ऐसा नहीं होगा.
ठीक है ना, ये ऐसा ही होता रहता है. चलो, और कोई और बच्चा बताएगा मुझे जिसने पढ़ा हो? Let me find out somebody else. I can see Divya Dhiman. दिव्या?
Yes, ma'am.
हाँ, आपको याद है?
No, ma'am.
नहीं याद है. अच्छा, एक मुझे यहाँ पे ध्रुवल सिंह दिख रहा है. ध्रुवल सिंह?
यस मैम.
हाँ, आपको याद है बच्चे?
ये मैम पीपीटी से करवाया था पर प्रॉपरली नहीं याद.
अच्छा, मतलब कोई कवर तो हुआ था पर हम भूल गए हैं सब, है ना? चलो ठीक है, मैं बता देती हूँ. मैं दोबारा से बता देती हूँ, अब की बार ध्यान से सुनना और ध्यान से समझना. ठीक है? Look, so far what we were talking about, logic 1 and logic 0. We always said we apply 0, we apply 1. How do we apply 1 and 0? Nothing is 1 and 0 in electrical engineering or electronics. These are only the notional digits. Okay. Actually, what are the physical quantities when you apply? Either it has to be a voltage, and or it has to be current. These are the two basic physical quantities which you can apply. Okay, so when these MOSFETs are typically voltage controlled devices, BJTs are current controlled devices, but still the input output voltages are important even in BJT, the current mode devices. So what we are talking about is when we say input logic 1 or input logic 0, or even if I'm not using any particular gate, इसलिए that is why I'm using a box. I have two inputs, let's say, and one output. So whatever I apply, 1 or 0, 0 or 1, anywhere, and whether I get a 0 or I get a 1, I actually get voltages. So what is the voltage range which can be taken as 0, and what is the voltage range which can be taken as 1 on input side and on again output side? That is what is very important. And voltage, these are called voltage ranges as well as logic levels. Okay, they decide your logic levels. Let me take an example. Let's say there is a gate which is driving another gate. So this is giving an output, and this output is taken as input. Okay. So what typically your voltage level should be when we are talking about these two? This is the voltage range on the two ends. One is output side, another is input side. So this is output side of this gate, and this is input of this gate. So if this gate is also, I'm assuming both the gates are operating on same power supply. So let's say this is VDD. So this is also VDD, and they are on the same level. And even the VSS or logic, low logic level is 0, or VSS, whatever you wish to write, no problem. So it is the same. Okay. Now this voltage can vary from 0 to VDD. You can have two logics. One is positive logic. In first year, we do not tell you, but actually it is so. There are two logics available. In positive logic, what we say is VDD, we say is logic 1. And VSS, we say logic 0. Whereas in negative logic, what happens is higher voltage is taken as logic 0 and lower voltage is taken as logic 1. Okay, so far you wouldn't have seen any circuit or anybody teaching negative logic to you, but you can design circuits using negative logic. Okay, so you should be aware of it, that there is positive logic and there is negative logic. Positive logic means high voltage, high logic 1. Low voltage, low logic, which is 0. Okay, negative is opposite. We are going to use positive logic all throughout, but I'm just mentioning so that you are not unaware of the term. Okay, and if a person like me asks a question in your next courses or during interview or somewhere, then you should at least be aware of that you have used a positive logic for your design. And there exists a negative logic, and what does it mean? Even if you are unable to design in negative logic, it's okay. Fine. So in positive logic, we say VDD is logic 1, and we say VSS is logic 0. But it is only in ideal cases. Typically, it is a range, which I will say, let's say I'm exaggerating, but still I am drawing two values. So this is output level. So this is known as VOH minimum. Output voltage when logic is high, what is the minimum value for it? So this is valid logic 1 range. So if your voltage lies between this, then it is a valid logic 1 on output node. Okay. Similarly, you have V output logic low max. Okay. And this range is the valid logic low range. Fine. I have purposely not drawn the two ranges to be equal in my diagram because they may be equal, they may not be equal in a given technology. Okay. So when I get an output from this gate, if it is logic 1, it will be somewhere voltage within this. And if I get a logic low, it will be some voltage within this. Okay, how do I know what is a value on the output node? You always need to read the data sheet. Okay, the data sheet of the IC tells you what is the possibilities, what are the minimum values available, what is the typical values available, and what are the ranges available. We will refer to data sheets later, but let me first define the terms. On input side, whatever value I apply, logic 1, if I'm applying, it should be acceptable as logic 1. So this, let's say, is acceptable as logic 1. Then this value is known as VIH minimum. What is the minimum level, minimum value of voltage acceptable as logic high on input side? Similarly, you will have VIL max. And for a technology, be it TTL or be it CMOS, because these are the two most popular technologies in the two categories, if they correspond to a technology, this will always be lower than this. This will always be higher than this. So this is forbidden. This do not exist. And this is intermediate, which is not acceptable. If this voltage comes within this range, okay, then this cannot be recognized either as logic 0 or logic 1. So how this gate is going to behave and what output does it give, we cannot predict it. So it's not reliable. Okay. So this should always be higher than this. And this defines your noise margin, because a signal was generated by this gate. It reaches the input of this gate through a wire or interconnection or on chip or off chip, and is susceptible to noise. So how much noise this can bear and still retain the same logic or correct signal, this is defined as the noise margin. So noise margin is NMH, noise margin for high logic level, which is equal to, I'm writing mod because magnitude is important, So VOH min minus VIH min. So this magnitude is important. Okay. Similarly, the second noise margin is NML, which is equal to VOL max minus VIL max. Is that clear to everyone? So this here is the noise margin. Okay. And if you talk about these logic levels for TTL, I want to finish it. I'll take just one more minute and I'll wind up. This for a 5-volt system, for TTL, this is 2 volt. And this value is 0.8 volt. No, this is, no, I have not said it correctly. This is, I think, VIH. VIH maximum is 2 volt and VIL max, this is min. VIL, this value is 0.8 volt. Okay. Whereas on output side, VOH min, which it gives is 2.4 volt, and VOL min, this value, which a TTL gate gives, is 0.4 volt. So it has a noise margin of 0.4 volt on both the sides. Okay. Whereas for CMOS, if you see CMOS, VOH will be 5 volt. VOL is equal to 0 volt. Min max I am not writing. You can put it. This is min. This is max. And VIH and VIL, min and max. For CMOS, this is 3.5 and this one is 1.5. If I have designed a symmetric CMOS circuit, this is what I get. So you will see the noise margin, high and low, both are 1.5 volt. So see the difference. One difference for one characteristics we had taken, which we talked about the voltage levels and the noise margin. And we have seen that TTL has a zero 0.4 volt of noise immunity only, whereas CMOS has a much higher noise immunity of 1.5 volt. So CMOS circuit are less susceptible to noise for a same technology. I think I'll not be able to take up any other characteristics. We are already late. Okay, so this is where I will stop. If there is any question I'd like to answer, else I'll take it up in the next class. Okay then. Yes. The question is, what do we do in case of tri-state logic? Tri-state logic only tells me that neither it is connected to VDD nor to ground. We will take up a tri-state circuit and we will discuss it. Okay, it only says high impedance node, neither it is connected to VDD nor to ground. So the voltage cannot be predicted on that node because it is not connected to any source. Okay, we'll talk about it. Okay, fine. Any other question? Do we have any other question? Okay, then I end the meeting and we will meet Monday.